Hello everyone, my name is Ahmed and I'll be going through the first part of our project which focuses on the suspended pipe pendulum system. So here we look at the suspended pipe setup where the pipe hangs from a strap supported by two forklift pins. This setup acts like a pendulum. The strap provides a friction at the contact point with the tines which prevents the pipe from slipping. This project focuses on the five key component outcomes: the normal force on each tine, the minimum friction force needed to stop the sliding, the pipe angular velocity and angular acceleration, the maximum tension in the strap. So as we can see on the right side, the diagram shows the actual suspended pipe setup, a free body diagram showing the forces, and a kinetic diagram outlining the dynamics, which we'll calculate in the next couple of slides and simulate. So in this slide, we'll look at the appropriate theories and principles. So this system applies to the classic mechanics. We start with the Newton's second law for translation and rotation to define the motion equations. So for linear motion, we use F is equal to ma, so force is equal to mass times acceleration. For rotational force, we use torque, so T is equal to I times alpha, where T is the torque, I is the moment of inertia, and alpha is the angular acceleration. For pendulum torque, we have T is equal to Rf sine theta. At rest, net forces in x and y are zero, which means that the sum of f of x and the sum of f of y is equal to zero. We also incorporate the centripetal force, so Fc is equal to mv squared divided by r, and related angular velocity to the linear velocity using v is equal to omega times r. The potential energy and the kinetic energy were calculated to track how the energy changes as the pipe swings. These were essential to validate the results in the MATLAB simulation and code later when doing it. So in this slide, we'll be talking about the boundary conditions and the final equation. So to solve the system, we assume that the pipe swings between 0 and theta 0, and there is enough friction at the tin to stop the slipping, and the pipe is stationary at its maximum swing angle. So from these assumptions, we develop equations for each physical quantity. So as mentioned in the previous slide, there were a couple of formulas that we used to drive and then came up with the final equations on the table on the right side. So this was also mentioned in the report, detailed as well in the part 2. And these equations were considered moment of inertia, pendulum motion, torque, and energy conservation. And these were applied directly in MATLAB for validation to check our handwritten results versus the MATLAB results. So this slide shows the initial MATLAB setup, which was labeled as task 1. So we use scripts to define things such as variables, constant, and input parameters, including mass, radius, length of the strap, and initial angle. So the parameters are mentioned on the next slide with task 2. This code calculates the reaction forces on both tines, so the angular velocity using the energy conservation, the angular acceleration using the torque equation, and the frictional force needed to stop the movement. The pictures on the left hand side shows the Newton's second law of motion, F is equal to ma, and the free body diagram. The picture on the right hand side shows the more detailed calculation and the verification using MATLAB. And the pictures on the bottom shows the Simulink block that was the code and the block that was used. So this setup serves as a base for both manual verification and the Simulink integration later. This slide will talk about the Simulink and SimScape model, which was labeled as task 2. So as previously mentioned, we had our parameters for each values in this slide, and then we also have our two uh, simulation models for Simulink and SimScape. So to better simulate the dynamic behavior, we build a system in the Simulink and SimScape model. For the SimScape model, Simulink model handles the signal flow and the dynamic blocks, while the SimScape model visualizes the real-world mechanical interactions using the physical blocks like masses, joints, and springs. So as we can see, the first block is the main block that was used to combine the two. And the first two pictures, and the two other pictures is the Simulink codes, that was the blocks that was used to map out. Each of those pink blocks shows the graphs, and then when we ran the Simulink model, we got the simulation, which was also mentioned, with the pipe pendulum moving, and then the last three, or the last two of pictures were used to do the Simscape model. So we can see the second picture has two different graphs in the pink, which was used to show, which will be seen in the next slide. And then the last, what we did was we wanted to compare these two, and so to see the difference in between. So the comparison shown highlights the difference in the model behavior under the identical inputs. And this step was very important to verify that the both approaches give the consistent result for each graph and the result that we used and how it is versus the handwritten results. So as my last slide, I'll be talking about the results we obtained from both models and the graphs in comparison. But we can see that the first two graphs on the left side is the Simulink graphs, and the bottom two are from the Simscape, and the two left remaining are the comparison. So the graph shows how the angular velocity and direction forces change over time. So from the Simulink output, we observed a sharp initial response, followed by an oscillation going up and down. And in Simscape model, the physical model showed the smoother than behavior. When comparing the slides, the graph side by side, we had the green as the Simscape model, and then we had the yellow line representing the Simulink model. And both models validate our calculation and highlight the real-world phenomenon like damping and inertia. And this shows the consistency between the two models, confirms the accuracy of our equation and our setup.
In task 3, we extended the suspended pipe system by introducing horizontal sliding along a surface. Instead of only swinging, the pipe can now move side to side, and friction between the pipe and the surface is modeled to replicate real-world conditions. The goal of this setup was to observe how friction affects the dynamic behavior of the system, specifically how it dampens the swinging motion over time. We used this model to examine both angular and linear motion and validate it using MATLAB and Simulink simulation tools. To build the sliding model, I used Simscape component like mass blocks, contact blocks, and joint to construct the physical interaction between the pipe and the surface. I calculated the position, velocity, and acceleration of the pipe's center of mass using symbolic MATLAB equations. These were used to compute force and angular motions. In Simulink, I used the pipe com and scope blocks to observe how the pipe moved in the x, y, and z direction over time. The simulation was run over 30 seconds to see how the pipe settled under the effects of sliding friction. The simulation result shows that both the angular and linear velocity gradually decrease over time. This matches our expectation. As friction resists the motion, energy is lost, and the system eventually stabilizes. From the graph, we can clearly see that the pipe starts with a significant oscillation, and then slowly comes to a near rest position. This confirms that the friction and motion modeling are working as expected and that our Simulink system accurately replicates the physical behavior of a damped pendulum with sliding. In task 4, we added the constraint to the system by attaching the pipe to the rigid rod and cylinder. This limited the pipe's motion even more, providing a more guided path for swinging. The objective here was to see how this added constraint impact the damping and swinging behavior compared to task 3. We expected the pipe to show similar decay in motion, but with more control over its movement, especially in lateral directions. To create this new system, I modified the existing Simulink model to include the planar joint and rigid connections to simulate the rod and cylinder. I used additional contact blocks and pipe components to measure the forces and motion in the system. The CYL scope blocks was introduced to capture data on angular velocity and velocity in x, y, and z axis. As with task 3, the simulation was run for 30 seconds and results were collected for comparisons. The results of task 4 show a similar damping patterns to task 3. However, because of the rigid rod and constraint, the swinging motion is more controlled and shows less side deviations. The velocity plots confirms that the pipe slows down steadily and reaches equilibrium faster. This shows that the additional constraint adds stability and changes the overall motion path, which is exactly what we aimed to verify with this extended model. Thank you. To validate our model, we compared our hand calculation with MATLAB simulation output at different angles. First, we used two angle inputs, theta equals 0 and theta equals pi over 12, and entered all relevant pipe and strap parameter into MATLAB. At theta equals 0, the results were very close, with just minor difference in normal force and angular velocity. When theta equals pi over 12, we again saw small but consistent differences, such as at 0.2 radians per second difference in angular velocity. They're likely due to MATLAB using floating point precision, exact geometry, and more detailed inertia handling. Finally, we checked two values that don't depend on theta, tension in the strap and minimal friction. The biggest gap was in friction force, likely because MATLAB includes dynamic effects and real contact models, whereas our hand calculation used ideal assumptions. Overall, the results are consistent and confirms the reliability of our model. Thank you.